welcome to Brahmagupta Physics Colloquium. Today it's a pleasure to have Professor Mayuri Rao with us. She is an associate professor at Raman Research Institute. She completed her PhD from Australian National University and subsequently held a prestigious CMB postdoctoral fellow at Lawrence Berkeley National Lab. She joined RRI thereafter as a faculty. Her primary research institute interest is on understanding the thermal universe and the methods to detect faint signals from the early universe. She is a principal investigator of the CMB DISTORTION Lab. Today she will give a talk on global signal measurement cosmology experiments at radio frequencies.
Great. First of all, thank you for having me here as a speaker. I'm really thrilled. Kind of slightly modified my title to be a little bit more appropriate, but anyway, we'll get into that. So the idea is that I will walk you through a few science areas that have relevant discovery space in cosmology, and then I'll focus on some challenges why these signals we're trying to detect have not yet been detected. And then I'll get into two experiments that we're running at our lab in RRI trying to detect these signals. Here, we also have a stream of undergrad and master's students who come through the lab through internship programs that they have contributed to some of the results that I'll be showing here. And we also have excellent support from our electronics and mechanical departments at RRI, as well as we have a field station where we conduct a lot of the tests that I'll be showing you. Instead, this is the kind of picture we see, okay? Any signal that comes to us from earlier and earlier in the universe, okay, comes to us through a screen which is presented by our own galactic emission. So that's what we call foregrounds in this terminology. And beyond our own galactic foregrounds, we also have to contend with forces such as our own Earth's atmosphere or ionosphere, radio frequency interference. So all of these are areas that we work on in the lab in an attempt to detect the signals that come from the early universe. So before I move on to that, this is a picture. You will see some version of this in any talk in cosmology. Let me walk you through this picture. So you would have heard of what we call popularly the Big Bang model in cosmology. And this is more in jargon, this is called the lambda CDM model. But essentially what that involves is there is some point, some singularity that we don't quite understand very well, and there are experts in the room who work on these areas better than me. But very quickly, within a few minutes after T0, when we think the universe kind of starts, the clock starts ticking, all the matter that is around us, this kind of matter, what you and I are made up of, which we call baryonic matter, is in the form of plasma, okay, protons, electrons, some helium nuclei, and trace nuclei of elements like lithium and so on. And there is radiation, okay? These are the two main components. Beyond this, there is dark matter, but we won't touch that for now. But we know that eventually the universe expands and cools down, and it cools down sufficiently enough for electrons to be captured by nuclei without getting ionized again because some other photon ionizes it back, okay? So eventually the universe expands and cools enough to form the first atoms, okay? Broadly, this period is called the Epoch of Recombination. That is the period when the very first hydrogen and helium atoms in the universe form. When this happens, the universe becomes transparent to the radiation that was bouncing around inside, and this comes to us as light today, okay? So if you had microwave goggles and you look up at the sky, the universe will be aglow, okay? It will be lit up. And this is what we call as the cosmic microwave background radiation. And today its temperature is about 3 Kelvin, okay? 2.72 something Kelvin. Eventually, what has happened to these atoms, eventually they start forming stars and galaxies. This period when the very first sources of radiation that you and I understand, stars, galaxies, etc. form, is known as cosmic dawn. That is one of the biggest missing pieces of the puzzle in our current understanding of the history of the universe. The other one being inflation, which I'm not discussing today. We don't understand when these first sources of radiation, stars and galaxies formed, how heavy they were or how big they were, how efficient they were in emitting radiation. But we do know that the radiation that they emit eventually goes back and reionizes all the neutral matter in the universe. So all that hydrogen and helium that had formed in the epoch of recombination was neutral. Then the first sources form and the radiation from them reionize it. So if you look at the universe on cosmological scales, what we call say 100 megaparsecs or so, very, very large clusters of galaxies, on average, the universe is mostly ionized. Okay, neutral hydrogen in the universe is an anomaly, it's an exception. We don't understand what happens during this period of cosmic dawn and epoch of reionization. But eventually, when we look out into the night sky today, we see there are plentiful of stars and galaxies, and that's where we're sitting after all the stars and galaxies are formed.
The sky is overall neutral.
Overall ionized.
On average, it's neutral.
On average, it's ionized. The universe is mostly an ionized place. So pockets of neutral hydrogen are very rare. So people try to find these pockets of neutral hydrogen in absorption.
Compensating electrons which are running around.
Yes, yeah. So it's plasma. It's plasma, yeah.
Can you explain what you mean by the universe being transparent to the radiation?
Okay, so when the universe, there's a concept called optical thickness, which is basically a different way of saying opacity. Okay, so during this epoch of recombination, you have mostly plasma. Okay, which means radiation scatters off these ions or electrons and nuclei. But once neutral atoms form, this process of scattering is much lower. So the universe becomes more radio transparent to that energy level, and that's what I mean by it becomes transparent. Okay, so this is the bigger picture. So this radiation, I said, cosmic microwave background, has been observed. It was detected in 1964-65, and initially when it was seen, it matched the prediction of Gamow et al. And this is what you would see. You would see a uniform glow more or less at 3 Kelvin. But there have been several measurements since then that have gone out and measured the spatial distribution of this cosmic microwave background to increasing accuracy and sensitivity. And this is our current picture, where you can see that there are tiny fluctuations around this 3 Kelvin. Some spots are hotter and some spots are cooler. And this lines up with the prediction of lambda CDM cosmology. So the cosmic microwave background detection and measurement is one of the cornerstones of the current cosmological model, or what we call the Big Bang model in general. This is a better picture. Yeah. This is what we call the cosmic dipole. This is just our solar system going through the cosmic microwave background that puts this hotter and colder effect. Is just redshifting. So this is a dynamical effect that we remove. This was the original measurement of the first few fluctuations detected at large scales by an experiment called COBE. It was a satellite that went up. So this is a different version of the same picture, where you put yourself at the center of the universe, because observationally that's how you see the universe. You look out into the sky and all around you there's a galaxy. Beyond that there's a cosmic microwave background and cosmic dawn, epoch of reionization. But one thing I'd like to point out, which is very interesting, is this kind of outer blue shell. There's a black ring there, which is called the black body surface, which tells you that at some point when the universe was sufficiently dense and there was sufficient number of scattering between these photons, electrons, and there were various processes such as Compton scattering, etc., that were very active because the timescales of collisions were efficient. The spectrum of the black body thermalizes to that of the spectrum of the cosmic microwave background thermalizes to that of a black body. Okay, so you expect the black body the cosmic microwave background radiation spectrum, so its intensity versus frequency, to trace that of a black body. Okay, and that is exactly what was measured by this same experiment COBE. It had an onboard spectrometer. And each of these points, I think here the points have been blown up to just for you to be able to see it. 1 to 1 part per 100,000, COBE measured the spectrum of this cosmic microwave background to be that of a black body spectrum. Okay, it's probably the purest black body you find in nature. Okay, and but that's not the end of the story, and that's why I'm here today, okay? If I go back to this picture, you find that after the CMB becomes a black body, okay, it's thermally relaxed, there are some energy injection mechanisms that can distort this black body. And these distortions in the black body spectrum should remain till date, okay? And these distortions in the black body spectrum have never been detected, but they contain a lot of rich physics about the early universe, about how the universe, the ionization and thermalization history of the universe. There's a lot of rich physics in there, and that is what we're trying to detect, okay?
The picture you showed earlier.
Yes, this one,
Even
this one.
so those dots are Planck distribution, temperature.
Yes, so this is only temperature. So each point you can think of as its own black body. It's a slightly different black body temperature.
You are saying now there is a distortion in the black body.
Yes, yes. And this distortion in the black body spectrum has never been detected, but it has been predicted by all standard models of physics. Some of them, even the amplitude of that distortion is very well predicted. Some it's not, and that's where the physics lies. Okay. So, like I said, this is the current best measurement of the CMB spectrum, and the frequency range is about, this peak is at around 150 gigahertz. So this was a space-based experiment, and in the Wien tail, it is very well constrained. It's a beautiful black body curve, okay? But in the Rayleigh Jeans end, which is here, sure, within some error bars, it's still a black body, but you can see that the error bars are much larger. Here, for context, the error bars have been blown up by like about 10,000 for you to be able to see those dots on the curve. But here, it's pretty clear there are large error bars, and sitting under those large error bars in the CMB temperature measurement, there's a lot of physics that can happen, and you can say that it's maybe not a black body there, and then what happens? So that's the kind of stuff we are going after at the radio frequencies, say 10 centimeter wavelength or so. So one of these physical processes that can inject energy into the CMB black body spectrum, and which should be preserved today, is the process of formation of the very first atoms, what I called as the Epoch of Recombination before. The idea is fairly straightforward. You have plasma, yeah. It starts before, it kind of finishes up towards the end of recombination. So what you see as the surface of last scattering is the tail end of recombination. Before, they start before. So if you see these spectral distortions, in a way you're probing beyond the surface of last scattering. Yeah. So, yeah. So for context, the surface of last scattering, or when you make an image of the CMB and those fluctuations you see, that is at an age of the universe when it's about 380, 400,000 years old. For context, today the universe is about 13.9 billion years old. So if you start from the early universe, it's like a baby universe, like 380,000 years is nothing compared to 13.9 billion years, okay? The process of the formation of the first atoms starts somewhere around like tens of thousands of years and finishes up around 380,000 years. So you're really looking at the super early universe, okay, infant universe, right? And okay, so let me explain quickly what these lines are and then move on. So you have protons, electrons, helium nuclei. Eventually things start cooling off, and your helium-3, doubly ionized helium, captures an electron in its outermost orbital shell. And then gradually that electron trickles down to lower and lower shells, and it forms some stable helium-2. Similarly, helium-2 captures another electron, kind of gradually that electron trickles down. Similarly, hydrogen is basically a proton. It captures an electron and that trickles down. Every transition, free bound and bound bound, emits a photon, okay? Of course, there are interactive processes between these various species. You know, the photon coming off of hydrogen may redshift and go knock off some helium electron from its shell, and there are these interactive processes. But you capture all of that physics in your simulations, and you put in some very reasonably simple cosmology, nothing super complicated because there are no astrophysical objects involved, no stars, galaxies. And this is the black solid line is what you expect all those photons to add up to. All those photons from free bound and bound bound transitions in helium and hydrogen are captured by this curve, okay? This is a simulation. This is the current best simulation of this process. And for context, for every atom in the universe, there are a billion photons. Okay, so each atom contributes about a photon to the existing bath of CMB electrons. So this signal is expected to be a billion times weaker than the CMB spectrum itself. So if CMB is 3 Kelvin, this is like 10 raised to minus 9 Kelvin in Kelvin scale. Okay, but this is an inevitable prediction of cosmology. There is no crazy physics going on here. If you don't see this, you're in big trouble. Standard cosmology is in big trouble. But you've not yet seen it because it is so faint, it's so weak. Okay, someone compared this kind of a measurement to like detecting the Higgs boson. You know it's there, you have to build this whole thing to find it, but it is there, and then that seals your deal in like particle physics. I'm not an expert, but that's what I've been told.
What determines that 10 power minus 28 is just the number density
Yes.
of hydrogen?
Yes, yeah. So nothing, everything is very standard. So the simulations are limited by your understanding of the atomic structure and substructure of helium and hydrogen. Okay, so there have been predictions even before that takes up to 10 shells, etc. I think this goes up to some 100 shells, and all the orbitals, suborbital, all that stuff goes into this simulation. Yeah. Yes, that's absolutely right. Yeah. So that with some cosmology thrown in, because there are some spatial length scales that you have to put in, because that's the mean free path of interaction. So that is the kind of cosmology that comes in, and temperatures of the background radiation. So all of that goes in, and this is the prediction that we have. This is the current best prediction. And this detection has not been made to date, but it is sitting there waiting to be discovered, we hope. So this is the first science goal, that one of the science goals that we're going after.
CMB will be the foreground.
Yes, exactly, yeah. So CMB is like a black body. Riding on that black body is this signal. Yeah. So next we come to the next stage where atoms are formed. There is this thing called dark matter we don't understand, but we do believe it collapses into these gravitational potential wells, which attracts baryonic matter to fall in. And then this starts igniting the first sources. The first stars and first galaxies form, or what we call first structures form. And that period initially when this dark matter is collapsing and slowly baryonic matter is interacting, we call it cosmic dark ages, because so far no sources have turned on. Everything is dark other than the CMB. There's no light. Then cosmic dawn, it's a very like philosophically beautiful and appropriate name, is when the first light from the universe begins. The first stars, first galaxies start lighting up the universe. They emit radiation, and the X-ray emission they emit starts heating up the gas around them, and that reionizes the universe back to being plasma. So it starts off at plasma, goes neutral, comes back to plasma. So this period is, like I said, among the bigger questions in standard cosmology. We don't really understand this period. It's very messy. The physics is very complicated. And this is what we want to study. There is some relevance to dark matter, because I'll discuss the signal what we want to detect shortly. But one of the parameters that determines what we see depends upon, for example, the critical mass of the dark matter potential well that attracts. So we can study something about dark matter. It's not a direct, we can't say what dark matter is, for example. But there are models that explain different, there are signatures for different models of dark matter, if we can put it that way. So this is the signal. It's a very complicated curve, but I'll just walk you through it. So what we're studying here as a function of frequency on the x-axis, or equivalently in time, or redshift, what we call, is the difference in the amplitude of the signal that comes from neutral hydrogen and background radiation. So it's a differential signal. So things go negative in temperature scale. Okay. Initially, so there are a few parameters I'll point out here very quickly, but that's not the important stuff. That doesn't have to be the takeaway. The amplitude of the 21 centimeter signal from neutral hydrogen. For those who are not aware, neutral hydrogen can emit a signal with a rest frequency of 1420 megahertz or 21 centimeter in wavelength. When the electron spin flips from being aligned to anti-aligned. So it emits radiation, okay? This is technically like a very slow and forbidden process, but because we have so much hydrogen in the universe, it's a great way to study the universe because statistically it adds up. This amplitude or the amount or intensity of this 21 centimeter neutral hydrogen from the universe, we characterize by what we call as a spin temperature. It's like an equivalent temperature, okay? This spin temperature by itself has no meaning because it's, like I said, it's an equivalent temperature. So it follows one of few things. It just goes along with the dominating physical process. For example, it can go with the kinetic temperature or the physical temperature of gas, matter, or it can trace radiation temperature, background temperature, okay? So what we're seeing here is this effectively here, which is spin temperature minus radiation temperature as some fractional quantity, multiplied by the total amount of neutral hydrogen in the universe, or neutral hydrogen fraction. So all the other constants are cosmological. We don't have to worry about them. So initially, hydrogen is coupled to matter because it is effectively matter. The spin temperature cools along with matter, and matter cools faster than radiation. So it gets dragged down compared to TR. Eventually, when the first galaxies sources of radiation formed, it kind of again kicks up because gas gets hotter, okay? So you have this excess that can go above the radiation temperature, and then eventually all the neutral hydrogen is gone, it comes back to zero, okay? So this is one of the, if you take some standard parameters for various astrophysical processes and put in standard cosmology, you get this what we call vanilla model. It's like a generic model. But because you don't, there is so much
So here you are showing the brightness of radio frequency waves, right?
Yes.
So why was till now the radio telescopes discovered earlier galaxies?
Yeah.
And why we are looking for the Webb images from James Webb Space?
Oh yeah. Okay, good question. So this is, first of all, this signal comes to us from the entire universe. It's not a specific source or a target. You're not looking at a specific galaxy. This is an evolution of the ionization state of the universe as a whole. And it probes much deeper than James Webb. So the James Webb, I think highest redshift, that's what they've claimed so far, is about 14. This goes like redshift, this is somewhere like, this may be 14. The signal goes all the way 20, 30, 50 something. So the signal goes much deeper, and I don't think we are expecting to image any of the sources that go this far. So the best way to study this early in the universe, these processes, is using hydrogen. James Webb cannot go this deep, and I don't think there's any telescope planned this deep. Yeah.
I'm not saying
Yeah.
James Webb would image. I'm saying why we haven't used radio telescopes to image our first galaxies.
People are trying. It's just a very, very weak signal. Yeah. And even that imaging, because it's so weak, what they're trying to do is not make images, because you can make images in radio. They're trying to do a statistical detection of, oh, there is more neutral hydrogen here, less here with time. So that is the current attempt. And that is what we call power spectrum measurement. This is a global measurement. It's not the statistical, it is on average, but you can probe much deeper and much longer in time. Yeah, but people are trying, yeah. Okay, so anyway, so the idea is this signal is complicated, and the specific shape and amplitude of the signal, if you measure and detect correctly, it can tell you things like when exactly the first source is turned on, what is the size of this gravitational potential well into which matter would have collapsed, how efficient the radiation was that comes out of these sources that reionizes the universe. So all of these parameters are uncertain right now. And that uncertainty is captured in this plot. This nest of multicolored signals are just some of the standard model predicted signals that come from cosmic dawn, epoch of reionization. It's like some 6-parameter problem. You change 1 parameter at a time, you can get any number of curves you want. And this is another signal that there's a competing experiment called EDGES. In 2018, they claimed a detection, and this is what they had claimed, which blows your standard signals out of the water, and all kinds of things, including some annihilating dark matter, exotic physics. Like physics had to change, not astrophysics. You had to invoke non-standard physics things like radiatively interacting dark matter. So those are the kinds of models, exotic models that had to be invoked to explain this signal if it was cosmological in origin. Edges is an experiment from US, yeah. So our group since then has countered this experimentally, saying this is not a cosmological signal because we didn't see it, even though we had the sensitivity to see the signal. So we have refuted that detection. So right now, again, this kind of has gone off the books. But anyway, so this is how open waters we are like kind of treading right now. So
You just said that you have not detected such a deep signal.
Such a deep or a class of such deep signals, yeah. Anything this deep.
You have not seen anything.
So we have constrained some of these models. We have ruled out some models so far, and we have rejected this and a class of models that are this deep and wide. So that has been done from our group. So yeah.
Was it a transient that it happened?
No, this is not a transient thing. Yeah. So there are reasons. I'll come to why we think they may have seen this, which is why this has been a challenging experiment. So these kinds of experiments to detect this kind of a signal have been globally running for the past 20-25 years, and there has been no confirmed claim detection to date. It's a tough experiment. So I'll tell you why it's so tough. No, they still stand by it because they tried everything to get that signal gone. They still see it. The only thing they had not tried before is to observe at a different site, because that could be some site-related thing, and now they're moving to Alaska. So this experiment is a US experiment, but operated in Western Australia. They're currently, I think, observing in Alaska somewhere, or yeah, I think Alaska. Okay, so why is it such a challenging experiment? Why have we not detected this signal or the other signal so far? The first is an astrophysical limitation. So anywhere you go, you do whatever you want with your instrument. Nature is not kind. Okay, so one challenge is, like I mentioned, our own galaxy is very, very bright. So at these frequencies, for example, this signal is about, let's say, 40 to 200 megahertz. The signal is about 10, okay, at the most 100 millikelvin in amplitude. Our galaxy can be a million Kelvin at this frequency. So it's like a 1 part per million at least detection problem, okay? And there's a lot of structure in the galaxy, okay? It's not a smooth, homogeneous thing that you just look through. It's messy. And this messiness translates into funny features in your data if you don't take appropriate care in designing your experiment. Okay, so first is a dynamic range problem. So just for context, this is the signal from cosmic dawn, 50 to 200 megahertz, 100 millikelvin something. This is like a clean patch of the sky. It's about 800,000 Kelvin when you look through an antenna beam. So you take an antenna, you stick it on the sky, and you average the entire patch of sky. You convolve the beam with the sky. At every frequency, you get one number, and that's what we call this frequency spectrum. And this is about some 1000 Kelvin versus 100 millikelvin, okay? This is the other signal from the first atoms, Epoch of Recombination, 2 to 7 gigahertz. Here, it's a little kinder, it's nicer, it's about 3 Kelvin, but unfortunately, your signal is tens of nanokelvin, 1 part per billion-ish, okay? So this is an astrophysical natural challenge. So is it even possible to detect these signals if you design the best experiment in the world? We think yes. And what we want to use to exploit, to separate what we call foreground from the cosmological signal is what you and I as humans quickly recognize. Oh, there are funny, interesting features here. There are like ups and downs and curves, but this is very smooth, you know. So can we use that as a basis to separate the cosmological signal and the foregrounds and say, yes, we can detect this? Can we do this on paper at least? So we have done that. So we have developed some basic mathematical tools and algorithms in our lab, what we call maximally smooth functions. There are some class of functions in maths like a power law that we call a complete monotone. Basically, there are no inflections. This is some variant of that where we allow for 1 or 2 degrees of inflection because we expect it naturally in the sky from, you know, our data, because you expect there is a power law coming from our galaxy. But once you do that, you stop and you don't allow any further inflections or ups and downs in the data. Okay, so we use that as a curve fitting algorithm, and with that we have been able to recover in simulations in our pipeline. So basically an ideal instrument, the signal that we put in, okay, to noise level, noise limited accuracy. Okay, so we have a mathematical framework in an ideal instrument case to separate the foreground and the signal in a data set, okay, which is an important first step. You should be able to do that once you get data. And the basis for this is exploiting the smoothness of the foreground and the non-smoothness of the cosmological signal, okay? And this is very important because not just are we using this in the data analysis, we're also using this as a basis to design all our experiments, okay? Because if your own experiment introduces funny features and shape in an otherwise smooth signal, you'll never be able to separate the two. So to retain the smoothness of the foregrounds, you have to make your instrument smooth over a large spectral range. Okay, so that is the basis of our design philosophy of all our experiments so far.
Why can't you do match filtering or something like?
We have tried. Yeah, we are trying. Somehow we have. Okay, one of the reasons it's a problem for Cosmic Dawn is that we don't know what filter to match to. Okay.
You have to run through many.
Yes, we will. Okay. So we have tried this. Somehow we have not been able to capture it as well as we would like. So this is, yeah. So some parametric model like this has been cleaner, with which we have been able to make some claims. But we are also looking into that kind of in parallel. Yeah. Yes.
So this is the.
Oh, this is just without. Yeah, this is just without the signal in the data. It's like numerical accuracy, and this is when you put the signal in the data. And I can assure. I hope here's an example of a plot. If I put in the signal, no matter what the order of this fitting polynomial is, I don't keep eating away at the signal, because if you just put a normal polynomial, unconstrained polynomial, the higher the order of the polynomial, the better it will fit to your signal. That's it. We don't want to do that. And interestingly, if you just take a power law, it will not do this. Because a sum of power laws is not a power law anymore. You can't use that function. So we have to come up with some modified smooth function, which is what this work was. Yeah.
Can you go back to
Yeah.
equations? What is the difference in the polynomial and this?
Oh, it's a very simple thing where we reject any solution that allows inflection. So basically, finally, it's a polynomial where you solve for coefficients. For every degree of the polynomial, we check if the coefficients, the solution it gives you, allows an inflection. Okay, yeah, point of inflection. If it does, we blow up the chi-square. We don't let it fit. So it's not an acceptable solution. We keep doing that over and over again till it fits somewhat. If the fit no longer converges, if it keeps coming back with the same coefficients, we know that that's how best we can fit it. So after that point, for example, here, this is what has happened. After some second or third order of this smooth,
Changing the polynomial.
yeah, no longer improves the fit. Yeah, so that's what's happening here. So we are increasing the order of the polynomial, but the coefficients are not changing anymore.
And you're doing for each of the pixels separate.
No, we are doing it for the sky spectrum, the whole convolved sky spectrum. Yeah.
So what is the issue with inflection points? Those derivatives appear in the denominator somewhere, is it?
I didn't catch your question.
Why are we afraid of inflection
Oh,
points?
because if it has inflection points, it will fit the signal.
Okay.
And that is the basis of us being able to separate the foreground from the signal. The foreground has no inflection. After we allow one inflection because we expect some curvature in the power law, but the foreground otherwise has no further inflections. That's all. So that is like some weird orthonormal basis. Just for those who are interested, the other basis people use are that your cosmological signal does not vary with time, but your foregrounds vary with time, because different parts of the foreground come into your antenna at different parts. So that is also being explored. Okay, so that's all the mathematical stuff for the signal detection. Now let's get to the experiment. This is a simple experiment in our books. This is the kind of telescope we build. We don't build interferometers yet. We don't do arrays. What we do instead is, because these signals are by definition, like I said, global signals, they come to you from all over the sky. You don't have to have any direction dependent sensitivity. You don't need like a beam and a pointing this way, that way. You don't have to do that. You just take a large, nice, wide beam, stick it on the sky and collect data. Okay. So here is the toy model. You have an antenna. It has a beam. It sits on some surface. It goes into what we call an analog receiver, which has filters, amplifiers, some calibration mechanism, and that is the key to the success of these experiments. You have to calibrate really well, 1 part per million, 1 part per billion. That goes into a digital receiver, which basically samples and digitizes this data and generates a spectrum out of it. Basically, it takes an FFT. And then you record it in some computer and analyze the data. Okay? But this is an ideal experiment. This is what happens in practice. Okay? For example, I'll just focus on a few things. Like I mentioned, the basis for a success of such an experiment is you maintain this smoothness in your data. Okay? Your instrument is not allowed to distort this smoothness principle. Okay? It cannot violate that. But all these effects, most of these effects I pointed out, in practice, make your data non-smooth. If your data is non-smooth, you cannot separate your foreground from the signal. You can never detect. You can never claim a detection. Okay? So, I showed you that our galaxy has a lot of spatial structure. You know, you have a galactic plane, you have these loops and spurs. It's a beautiful place. People make it their livelihood to study the galaxy, but for us, it's a foreground, it's a problem. Okay? What happens when you stick an antenna on the sky and that antenna's beam changes as a function of frequency, which means at one frequency, I'm looking at, let's say, the galactic center. At another frequency, I'm looking away from the galactic center. Okay? At frequency number 1, I have a very large amplitude. At frequency number 2, I have a low amplitude. And at frequency number 3, if I go back to the galactic center, it goes up again. Okay? And this is not because the data has non-smoothness. It is because your antenna beam is moving around. Ideally, you want to stick an antenna on the sky which looks at only one patch of the sky for indefinitely long and for the entire frequency range. Okay? That will give you a smooth spectrum. But if your antenna beam changes with frequency, it introduces shapes that are not real. Okay?
Do you have control over that?
No, not quite. Not quite.
No, that's very bad.
No, we do that. We do those kinds of things. We go to very remote locations, which I'll show you. But it's not as much as a physical vibration as much as just electrical properties of the antenna, where it is, the beam does not behave correctly over a large range of frequencies. So it is possible to design antennas like that, which is what we do. But we have to take care that we design such antennas. Yeah. Okay. Then the antenna sits over a certain surface, which means it's not operating in free space, which is easier and ideal to simulate. We do simulate the antenna on water, on soil, on surfaces where it sits, taking measurements of the local soil properties. But you can only do so much. But your antenna, because it operates at these long wavelengths, the electrical signals it picks up goes all the way down to several layers beneath the earth. Okay, so that changes again antenna properties, which are hard to simulate and model. Not necessarily time-dependent things like tremors and earthquakes, but let's say you have stratification. You have bedrock, you have water, you have another layer of soil with varying electrical properties. That means your antenna's properties also change, because antenna is finally kind of like a piece of metal operating in an environment. If the environment changes, the overall electromagnetic properties of the antenna change.
So if it rains, it's affected?
We see it in the data. Yeah, okay. So then you have standing waves. You take a piece of cable, you send a signal, physics 101 or school, whatever, you take a rope and you do that, it has standing waves. Same thing happens to electrical signals in a cable. So we see that. And standing waves by definition are not smooth. It's like a sine wave, okay? Then you have ionospheric effects, which does the same thing. Ionosphere can refract, reflect, absorb radio waves. Again, that's a problem. You have dynamic range limitations in your receivers, okay? You have RFI from terrestrial sources. RFI is radio frequency interference. So over all these frequency ranges of the experiments I discussed, you have FM transmitters, you have satellite, dish TV, you have communication links, you have God knows what. And you have errors in data analysis that can kind of corrupt. If you don't treat your data right, you will see things that are not there, or vice versa. Okay? But broadly, I've classified this into like the pink and the blue. The pink is stuff you have to do right, or you will see anywhere you go. You have to do justice, you have to design your experiment and analysis well. But the blue stuff, interestingly, is something you can get away from if you operate in different environments. And by that, I mean, for example, let's focus on this signal now. This is the one that, next few slides will be this till I change gears. This is the cosmic dawn signal. So over the frequency range of say 100 megahertz or so, we believe that the far side of the moon is radio quiet, the side of the moon that you and I don't see. We believe it is radio quiet, and this has been confirmed both by simulations as well as measurement at lower frequencies from decades old satellites. It is radio quiet to the terrestrial RFI. So if you put something on the far side of the moon and it is emitting RFI, you're doomed, and that's happening. But at least for the most part, more than Earth, certainly the far side of the moon is expected to be radio quiet. The moon blocks out interference from Earth. You can go to the near side of the moon and receive FM radio if you want to try. It's possible, or that's been tested. We have seen FM radio signals reflected off the moon and come back to Earth. That has been measured. Okay, so it's not great. Distance is not the problem. You need something to actively block interference.
So far side of the moon also a black body at that temperature. Any measurement of that?
So the moon itself, so Earth and moon themselves are like kind of black bodies, like some 300 Kelvin, 200 Kelvin. But what the black body I was mentioning is the temperature of the universe, free space.
Good, other side of the moon.
Yeah.
Somebody looks at what is the black body temperature.
Yeah, so moon has a surface temperature of about 200 Kelvin or something like that, like a black body temperature. Yeah. All right, so the moon, the far side of the moon is a good place to be to conduct an experiment if you want to be in a radio quiet zone. And if you want to truly be in a radio quiet zone without all these problems I discussed, you want to be orbiting the moon and taking data when on the far side of the moon. Okay, so you don't have coupling effects to the soil, etc. Lunar surface, which we call regolith, we don't have to model. There is no ionosphere to speak of, and it is radio quiet. Okay, so keeping this in mind, we had proposed an experiment called PRATUSH to ISRO a few years ago. So this is like a concept diagram of PRATUSH where it is making observations of the radio sky. This is what we envision our experiment to look like. And it's making measurement when on the far side of the moon in orbit, in the shadow of both the Earth and the sun, because the sun is also radio loud. There are flares and all kinds of crazy things going on. So this is when you want to take data. So very quickly, this experiment, we had originally proposed it to 40 to 200 megahertz, but currently what we are working on goes from 55 to 110 megahertz, because 1 octave in frequency is more manageable from an instrumentation point of view. It's a lunar orbiter. We have a lot of legacy from the ground-based experiment called SARAS, which had these results that I was mentioning earlier. We've got funded for what we call pre-project studies phase, and we expect to fly it as a dedicated craft. So we don't want to be sitting with other instruments that may be radio loud, because we can control our own emissions and some spacecraft emissions, but it's harder to do that with more complexity you add on instruments. And just from the launch opportunity point of view, we hope to fly this in 2 phases. Ideally, we just want to go to the lunar far side, but it's hard to justify that to a funding agency or ISRO. So initially we proposed
dimensions of these.
it's about a meter. Yeah, because corresponding to the wavelength, we can't go smaller. We came very close to getting a ride on Chandrayaan 3, but then they gave us this much space, and there's no way we can make an antenna at a meter wavelength this small. So we expect to fly it in 2 phases. Phase 1 in Earth orbit, where we think we can do some interesting things, but really for the gold, we have to go behind the moon. Okay, so this is the concept picture, and that's what it looks like in the lab right now on testing phase. Clearly, this is not like a standard looking antenna. It's not a parabolic dish or a dipole or something. This is a custom designed monopole antenna, a monocone, what we call. So you have a dipole, which is like, say, 2 arms that go to a differential cable. You take one arm of the monopole and you make the other arm like a reflector plate. You create a virtual ground. Okay, that's a monopole. You take that one stick of the monopole and make it fatter, it becomes wideband. Because a monopole is resonant at 1 frequency, like a dipole. But you want to make it broadband, you widen that antenna. That's what we've done. And you shape the reflector to get the correct properties in antenna beam, as well as the antenna, what we call return loss, or the way the antenna signal feeds into the receiver, how well it's impedance matched. Because even that is an important property. You want it to be smoothly impedance matched over the whole frequency range. And you have to do this entire design in the presence of another big chunk of metal, which will hold your electronics and spacecraft electronics and some power generation stuff and so on.
Is 3.5
Yes, so this is the feeding point. So this is after a lot of trial and error, passing it through a validation pipeline that we have written for feeding in our cosmological signal, sky model, iteratively, we have come up with this design for a bus of certain dimensions. So if and hopefully when ISRO selects us and says, okay, you guys can go, and they give us spacecraft CAD model, we go back to the drawing board and redesign this antenna to have the same correct frequency independent properties in the presence of that bus. Okay. And inside this, we have the analog electronics, like I said, the calibration, digital electronics, and spacecraft electronics. Two big challenges that we are currently working on, and if bright minds in the room, please help us if you have ideas. One is we have self-generated RFI. Okay, so you go all the way behind the moon, it's beautiful, radio quiet, and then you're the guys making the radio noise that you're picking up. You're not going to detect the signal. Okay, so you have to shield your electronics to about 120 decibel. Okay, that is how radio loud electronics can be, especially clocks, etc. on your receivers. So you have to minimize the electronics noise, EMI, interference, and you have to protect, encase this entire electronics in some fancy dabba, basically. Okay, and we're working on that. Materials engineers, everyone can pitch in. Okay, the second, again, yeah.
How much time on average do you get for one orbit?
Great question. So we expect an orbit of 2 hours, and the longest we think we can get is when it's full moon on Earth. So that's about 45 minutes. On average per orbit, on average, we think it's about 20 minutes. And we want about 100 hours. So in 2 years, we'll get enough data. The 100 hours is our kind of requirement. It's overkill, including, yeah.
Did you consider whether it's worth it to go for very low performance electronics with slow clock speeds so that you can reduce the radio emissions?
Well, we at least have to sample at like Nyquist rate. So where our maximum, our bandwidth is 55 megahertz. So at least 110 megahertz is what we need minimum to sample. It's none of this is very fast. It's about maximum we go is like 125 megahertz clocks. But then those clock lines have harmonics and subharmonics that kind of feed back into our band and lift the noise floor up. And that's the problem. But yeah, there are some tractable solutions, like where you keep flagging some channels and do some polyphase filter bank stuff and so on. But still, it's very loud. The other challenge is if you have this beautiful antenna structure you designed and you've thought about it, it does everything right. It's maybe like a piece of aluminum that's in this shape. It's orbiting the moon. It goes in and out of plus minus 250 degrees Celsius, so 500 degrees Celsius thermal swings. And that's going to warp this antenna, okay? And that's going to change the beautiful beam you are designed, and you're no longer seeing all those properties that you worked so hard to get, okay? So again, maybe a possible solution could be some materials engineering based clever material that has lower thermal coefficient of expansion and so on. But these are the two biggest R&D problems for this that we are worried about. Everything else we think we have solved or can be solved, high TRL stuff. So, but with all that in mind, we have gone ahead and built this for a laboratory demonstration where we have put in all the electronics, done the calibration, chosen components that are more or less have high technology readiness level. They have some counterpart space qualified stuff, and it's running in the lab, okay? So this is some pictures of what it looks like on the inside. I'll quickly come to what it involves a little later, but that's like a average human adult for scale. So it's this big with the antenna and everything else.
I think you mentioned you wanted to look at one part of the sky, but now...
Yeah, so the idea is at each instant of time, you want to look at one part of the sky at all the frequency ranges. That's what we want to go for, because clearly you're drifting or the sky is drifting or your antenna is moving around. So it's not versus time that you're worried about. It's at every instant of time at all frequencies you want to stare at the same part of the sky. That's a better way to put it. Okay, so this is again some tests we run in the lab. So the kinds of things we do is when we run this in the lab, because Bangalore is so radio loud, you can't really connect an antenna and do tests in the lab. So you can qualify your receiver separately and then put in your antenna later in a field where it's radio quiet. So we instead replace the antenna part with something that simulates an antenna. You put a RLC termination, basically some shape that has similar matching properties to the signal, to the antenna's performance. You terminate that with some 50 ohm load or something. And finally, what you're measuring is actually the behavior of the electronics itself. Okay, and these are the kinds of tests we do in the lab. And we have done this kind of a test with the PRATUSH receiver in the lab for like about 45 nights, about 8-hour nights. And we have followed more or less for the most part what we expect the noise curve to be. What we call, this comes from something called the radiometer equation, which more or less says that as you average with time, your noise goes down as 1 over square root time. And we see that trend. This is what, that's the 1 over square root curve. The red curve is the whatever fit, and the blue curve are the measurements of the noise. So we are following this trend for the most part, some deviations here which we think may be some RFI flagging related stuff. So this is like an average noise curve that we are seeing. So we get the data from our receiver, keep averaging over many nights, and keep fitting it with that smooth function I was telling you about. And we've gone down to about 3.4 millikelvin in the noise level in the receiver over 45 8-hour nights. Room temperature. Yeah. So this means that this gives us confidence that the electronics we have built in the lab has the sufficient sensitivity for detecting the signal. Okay, just the electronics. So the next plan is you put all your electronics in a better EMI shielded enclosure and put your antenna on top and go out to the field, and that's what we'll be doing shortly. Okay, so that's the other signal. So this one, I'll just remind you, this is the cosmic dawn signal when the universe first stars and galaxies form, 40 to 200 megahertz, 100 millikelvin or so. Yeah. So if you go to about a few millikelvin, that's the range you want to be in sensitivity. So just very quickly, I've lost track of time. I don't know how much time.
6, 7 to 10 minutes.
Okay, that's good. Yeah. So anyway, so these are all everything in red here. All these maroon curves have been ruled out by SARAS, our ground-based counterpart experiment. And these are our sensitivity predictions from some simplistic assumptions of RFI in low Earth orbit, the blue curves, and the combination of blue and red. So more or less most of the parameter space of standard physics we think will be sensitive to in lunar orbit. So very quickly, so we have taken this one step further just to explore the possibility of doing this in space around Earth. You will see a lot of RFI from especially FM. But again, you're in free space, you don't have these messy antenna properties, and you don't have ionospheric effects. So we have gone and built a model, and this is one of our undergrad interns who worked with us for a summer who built this model. And we have a model predicting the FM-based RFI in space at different orbits, different heights, different locations, different beam patterns, what you will see. And this is like a heat map at one frequency. This is like kind of the RFI occupancy map in time and frequency as you propagate a satellite in orbit. So we do think there are some kind of clean patches, the dark blue stuff here, where potentially you can make even a signal detection claim if it is truly radio quiet. But there are other sources of RFI like, Starlink does stuff that it's not supposed to do at low frequencies, other moving sources of RFI. So it's still not really this clean, but it's a first attempt that we can demonstrate to funding agencies and space agencies saying, hey, either we detect the signal, great, we need to do better, or look, this can never be done around Earth, we have to go to the far side of the moon. So it's a good demonstrator experiment. Okay, now in the last 4 minutes, this is the other experiment that is trying to go after this nanokelvin signal from the first atoms. Okay, the experiment is called APSERa. And very quickly, I showed you this black curve. That's what we were discussing. Comes from all atoms, all the transitions. But if you want to do a ground-based detection experiment, so I'm no longer talking about a space-based experiment. If you want to do a ground-based detection experiment, the best frequency range we have identified from a signal-to-noise ratio point of view is an octave frequency range between 2 to 6 gigahertz. That's where your signal to noise ratio is maximum, where you put in atmosphere, you put in your foregrounds and so on. And here the signal is about tens of nanokelvin in the 2 to 4 gigahertz frequency range. And this is the signal that this experiment is going to go after. Eventually, it will entail building an array of many radiometers just to add signal to noise ratio, just to build up the sensitivity. Not to operate as an interferometer, mind you, but just to you want that 1 over square root time to go up. So instead of you can increase time and number of receivers, which adds up to time basically. So that's the plan. But we start off with one prototype. And that prototype that we're currently building and getting close to deploying in the lab, we'll do this kind of science where I showed you this Rayleigh gene part of the CMB temperature spectrum that's very poorly constrained. And there have been some other signal detection claims that indicate kind of, again, exotic physics that could be sitting in these error bars. So you want to minimize the error bars. If there is something truly non-standard there, you will see it if you minimize the error bars. If not, you're on your way in the ladder of sensitivity building up to making this nanokelvin detection, right? So that's what this first radiometer is going to do. It's going to make a very, very precise measurement of the CMB temperature spectrum over 2 to 4 gigahertz. Right, so I won't get into this, but this is one of the experiments, RK2, that had claimed one of these exotic detections at radio frequencies, which is highly contested. And this is one of the models that was used to explain the edges signal. So it is not trivial. You know, there are implications for a signal like this existing that could explain the edges signal. So we have to go out and look for it and actively find it or reject it, which has not yet been done. So we're working on that. So we make custom antennas for this. Again, same rules hold. You want a frequency independent antenna with a smooth return loss over the entire frequency range of operation. And standard antennas cannot do this because they either have a sharp resonance in their band or their antenna beams are not frequency independent enough. So yeah, my student Kirti, she has led this work. We've designed a really nice, beautiful, compact planar antenna that can be printed on a PCB this wide, as big as my hand, can get scaled up if you need, you know, reasonably well in a PCB fab. And it is, we have found that the residuals that we expect on fitting these smooth functions is about at the level of millikelvin. So it will reduce those error bars in the CMB temperature spectrum if you do your rest of your electronics right.
So the frequency range is a few
2 to 4 gigahertz. Yeah. And this is our calibration scheme. It looks a little dense, but it's a standard for those who are aware. It's a Dickey switching radiometer. It switches between your antenna and a known source or load. So we switch between an antenna, a noise source, an electronic noise source, a cold load and a warm load. And we cool the electronics for this experiment because at this frequency range, your sky is reasonably cold. Your electronics are hotter than your sky. So you have to cool your electronics. When I say hotter, I mean the equivalent temperature of electronics. So we used cold receivers in our lab, and that's something we have started building. Challenges I've already discussed in general. And this is the kind of setup we have right now in our lab. This is another student of mine, Narendra, and this is our cryocooler in the lab getting commissioned. So a few months ago, we hit 77 Kelvin, and we've been hitting 77 Kelvin consistently. It's a commercial Stirling cooler that we use, and there's a turbo vacuum pump that backs it up. So a lot of work went into things like vibration isolation, because you'll see that as noise in your data. And another undergrad who interned with us built a really nice software interface that controls all our electronics and gives us a nice panel where you can look at all your data. Okay, and in the back end we have digital electronics, and these are the experts on that in our group. Right now, in both our experiments, we're using boards that we built at RRI, designed and built at RRI, based on the Xilinx Vertex 5 and Vertex 6 platforms. But now we're in the process of transitioning to an RF SoC based board for those who are aware. This is the latest cutting edge stuff in FPGA technologies, really impressive stuff. So that's what we are switching to for this experiment APSERa in the near future. Okay, so last 1 minute. Other stuff we need to do is we go out to all kinds of places, including our own field station, 80 kilometers from Bangalore, a place called Gauribadnoor, where we do all our initial tests of electronics on the field. But then for actual operations, we first go out and do an RFI survey. We've gone to Ladakh, we've gone to the Arctic in the winter, and our group goes out, or one member from the group goes out and does these RFI measurements. And then we come back, look at the data quality, look at the site quality, and quickly go back and do a deployment, because radio site quality worsens every day. Yeah, so we've also been doing other kinds of interesting stuff where we look at the atmospheric water vapor in regions around Ladakh to find a good site for the high frequency 2 to 4 gigahertz experiment, because at those frequencies even your own atmosphere adds up noise in your data. It adds noise temperature to your total system. Okay, so this is the kind of work we do in our lab. I had a few slides from some other work, but I'm going to skip it for the interest of time. But yeah, this is work involving using bolometers for higher frequency CMB detection experiments, inflation, and so on. But I won't touch that. But overall, this is a summary. There's a lot of rich physics in global cosmological signals. The kinds of things we are interested in our lab are signals from the epoch of recombination, when the first atoms form, and cosmic dawn, when the first stars and galaxies formed. They're extremely faint signals, but they have a lot of rich physics. And in the process of trying to understand these signals, we also end up modeling the galaxy, our own ionosphere, atmospheric water vapors. All of this is part of the job, and we understand new physics about them too in the process of trying to getting rid of them. And we do a lot of cutting edge instrumentation as well in the lab to detect these signals. So I'll stop and take questions.
So do we need to make those measurements right during the lunar eclipse for optimum results, or?
Not lunar eclipse, because when you do lunar eclipse, moon is between the earth and the sun, and you can see the sun. Full moon is our best shot. But that's not enough time. So we think we'll go 2 years in orbit, and we get the longest continuous observing time during the full moon phase. But we get about 5 minutes here, 10 minutes there, 20 minutes there. So it'll add up. But it doesn't have to be continuously 100 hours. Yeah. About called mu and by distortions, which are also expected. But so effectively, this black body may have something like this. So it's not really a black body, but slightly modified black body, on top of which there are these things. And each of this has some physics in it. So people are trying to detect that as well. Yeah.
So in this 3 to or few gigahertz range of CMB measurements, temperature constraints, which of these parameters, the distortion parameters, will it restrict?
Okay, so yeah, so what we're looking at in that frequency range is basically some the bound transitions between shells 15, 14, 13, 12, etc. That's what we're looking at those frequency ranges. But the kinds of cosmological parameters we'll be able to constrain are, first of all, the time axis of thermalization, because this is a time dependent information. Every peak encodes a time stamp. So that's why this is very, very rich in that sense. Beyond that, if you can actually go beyond detection and go to a measurement space, baryon density, actual CMB monopole temperature, they all change with those parameters. But that is, I don't know when that may happen. Yeah.
Well, you mentioned about adding the signal in time to reduce the noise.
Yeah.
What is the time scale of which the signal would vary, and what time scale should you add there?
So the signal does not vary with time, but what varies are foregrounds, because either your instrument is moving or the sky is moving. So the data comes out every second. So within a second, we don't expect the beam to have changed so much that is looking at an entirely different part of the sky. The cadence at which we capture and calibrated data is at every second. So that's the kind of rate we average. Yeah.
So like back on this question, like, is it the in-mode analysis that you're talking about? This foregrounds not changing with time, but the signals changing?
What analysis? I'm sorry?
In-mode analysis.
Oh, I'm not quite sure I know what that is, but we can chat later. Yeah.
Okay, so if there are no further questions, we can thank her.
It's a small memento.
Oh, thank you so much. Thank you. Thanks a lot.